First of all, let me introduce my company. Mail.ru is the largest internet company in the Russian-speaking world, and our search engine is one of our main business, and it's a very young project. We done the major part of our search engine was developed during the last 3 years, and now we are searching on Russian search engine market with 9% of market share. And in order to achieve such good results, we developed a lot of optimization techniques that helped us to save a lot of resources. And today I want to talk to you about one of these techniques that's related with ranking formula. But before, let me talk a little bit about premises of this solution. I think that there is no to prove you that today machine learning plays a significant role in information retrieval science and practice. And for example, our search engine have machine learning algorithm in all parts and major part of these algorithms are supervised. It means for us that we need to have some training set, and it's problem. It's problem because judgment is actually expensive task, and for example, in order to build high quality ranking formula, we need to judge about 1 million documents, and how you understand, it's really big number. And my opinion, and what I want to talk to you today, is that the size of this training set is motivated not only the complexity of ranking problem. This size is also motivated by a lot of problems in the data, and the first evident problem is that assessors are human, and human makes mistakes, and there are some solutions of this problem, but it's not my point today. And today I want to talk technical problems with this data, and in order to show you these problems, I made this simple example. We here see some two-dimensional space with points on this space, and some points are already labeled. It's points of red and green classes. For example, it's irrelevant and relevant documents. And also we have some number of unlabeled points. Yeah. It's clear. And the first problem is that there are some points on the border between classes. It's a problem because when we build classifier, we can make a wrong border between classes, and as a result, we obtain problems during classification of this problem. We obtain error, and in order to prevent this situation, usual approach is to increase number of examples labeled in the training set. And today I will show you other solution of this problem. The second problem is imbalance of labeled point in classes. You see that we have two clusters of labeled points. There's a cluster with red points and cluster with green points. And it's evident that number of points in red class is too big. We can drop out half of these points without loss of quality, and it means for us that we done a lot of extra work with our assessors, and we spent money on it. And the problem with second class is that this class have only 3 points, and maybe it's not enough to make a good classification. Of course, it's 2 examples, but this example demonstrates the problems. And the third problem is that there is a cluster with completely unlabeled points, and of course you can't say nothing about label in this cluster. And you may decide that this cluster is green, but for example can be red, and as a result you obtain problem. And my point is that the problems, that reason why do we need such big training sets is due to these problems. And we applied so-called active learning technique the idea of active learning to solve this problem? The idea of active learning is that we can smartly select a point before labeling. We can fix all this problem by selecting points in the proper way before we label this. And as a result, we save a lot of assessor working time, and our training set will be smaller, and the quality of solution will be the same or better. And today I want to show you how we do it for ranking. First of all, I explain how we solve problem with points on border, and after that I will show you how we fix problem with density, and at the end of presentation I will show you final solution, complete solution, and results. And our first experience with active learning was not in ranking. Our first experience was when we several years ago developed algorithms for sentence boundary detection, and at that time we had only one assessor for this problem, and in order to save working time of this assessor, we applied technique that's called uncertainty sampling. And the idea of the uncertainty sampling is following. Let's assume that we already have some labeled set. It can be a very small set that don't allow us to solve problem in the proper way. For example, we select, for sentence boundary detection, we selected about 100 points and label these points. And after that, we build some classifier. In my example, it's a solid blue line, vertical, that divide our classes. And the idea is following. We can check every unlabeled point, yeah, and we can measure distance from this point to the border. And it's evident if we want to improve precision of our border, we should take into account point around this border, yeah. And in this case, we see that point number 1 located near to border, and we select this point. After that, we label this point, and we put back to training set this point labeled and repeat this procedure. And after several iterations, we increase training set. The growth of training set size is slow in this case, but improvement of quality will be high. But this approach has one problem, that we need some measure of uncertainty. Usually, uncertainty measure used posterior probability that we can take from our classifier, and unfortunately, not every classifier can provide for us this probability. And the second solution of this problem is so-called query by committee methods. And the idea is following. Instead of one classifier, the same situation, but instead of one classifier, we built a set of classifiers, and each of these classifiers is committee of classifiers, and each of this model solves the our original problem. Yes, each classifier divide our classes, but all these classifiers have different parameters. Yeah, in this example, I changed slope, for example, of lines. And the idea is that for each point we can measure how many different words this point have. Yeah? And if all classifiers in committee agree about class of some point, it means that for us that there is no problem. But if some points have, for example, half of words in one class and the other half is another class, yeah, it means for us that it's a problem. And in this example, we have problem with point number 2, and we select this point. The advantage of this algorithm is that we don't need any posterior probability, and actually we can use any possible classifier, decision tree, neural net, support vector machine, and so on. It doesn't matter. And how we can understand, it's just idea, it's not a concrete algorithm, and in our ranking problem we used algorithm that is called QBack, and you can find description of this algorithm in the work Decision Tree Instability and Active Learning. And idea of this algorithm is following. In order to build committee of model, we use simple bagging technique. Yeah, classical technique. And the idea of bagging, for each model and committee, we just resample our original training set and build model. When our committee is complete, we just check every point in our unlabeled set, and for each point we measure disagreement. We measure how many different words these points have, and we select a point that have maximum number of different words in the committee. We select only one point, and after that we send these points to assessors, update our training set, and repeat this procedure until convergence. Please note to think about this algorithm. The first thing is that this algorithm is for classification problem, and ranking is usually classical ranking. Classical solution of ranking problem is based on regression. We try to predict some value of relevance, yeah, and it's not a classification. In order to apply this algorithm for ranking, we change our view on ranking problem, and we say that ranking is when we have two documents and we need to decide which document is better, one or two. Yeah, it's very easy to implement. We just take pair of documents that are found for some query, and this pair can be in two states, yeah, one or two. And the second point about this algorithm is that on each iteration, original algorithm select only one point, and after the selection of this point, we need to rebuild committee. And rebuild of committee is very complex task, yeah, and in order to run this algorithm in production, we need to run this algorithm in so-called batch mode, when we select multiple points by one committee. This technique, we obtain again problem with density because we can select a lot of similar pairs of documents. And let's see quality of this algorithm. The first curve denoted by squares corresponds to traditional random sampling when we sample documents from some pool. Horizontal line is a fraction of pool examples labeled. Yeah, it's size of our training set, and vertical line is some error of the obtained solution. And you see that the convergence of the random sampling is slow, and second line denoted by triangles corresponds to uncertainty sampling. You see that the solution is significantly better. Yeah, and the third line denoted by circles is correspond to Q-back algorithm that we use. And you see that first of all we need in 6 times more number of training set examples in training set in order to achieve quality of random sampling solution. The first thing, and the second thing is that we need in 3 times small training set size in order to achieve convergence. This algorithm really works, and this algorithm really saves a lot of assessor resources. And the second problem is density problem. Again, I recall you. We have dense region with a lot of points, and we want to drop out some of these points. We have sparse region without enough amount of labeled points. We have completely unsampled region, yeah, and we applied so-called clustering technique in order to solve this problem. We use so-called self-organizing map, also known as Cohonan map, SOM map for short. And the idea of this method is following. This image illustrates clusterization of our training set for ranking. You see that there is each point on this image is cell. Do you see cells? Yeah. Each cell is a cluster, and color of cell denotes the relevance of documents that belongs to this cluster. And clusters are topologically ordered in two-dimensional grid. It means that if two clusters are neighbor on this map, it means that these clusters are also neighbor in clustered space. It's not very interesting for active learning property. The more interesting representation of this map, it's again the same map, but instead of relevance, the color now denotes density of the cluster. The density is defined as average distance between clustered centroid and members of this cluster. And you see that we have area with high density. Yeah, we have some part of our space where there is no problem with density. We have enough documents. And we have a lot of space where density is low. And moreover, you see that there is some region with white color. It means that in this cluster we have no documents. We have no documents from this cluster in our training set. Yeah, and actually it's a problem. And our first solution of this problem was just to take such sparse cluster and find new documents from these clusters and add these documents to training set. We do this procedure and obtain following result. It's again the same map of our training set, but now color demonstrates generation of data that belongs to the clusters. The blue color is all documents that already was in our training set, and the red color demonstrates new documents that we selected from sparse clusters. You see that we have, I can say that we have two meta clusters. Yeah, we have big meta cluster of all documents, and we see that new documents form separate meta cluster. For me, it means that formula that is built on the old training set know nothing about these new documents, and as a result we obtain a random ranking for these documents, and actually it's a problem of ranking. And the second way how we can improve density problem, how we can solve this problem is following. We again build clustering. Yeah, we compute average density of clusters on this map, and after that we, for each dense cluster, the dense cluster is when density of the cluster is bigger than average density. For each dense cluster we limit number of examples in this cluster. It's a very simple idea. We drop out some examples that we do not need, and we obtained following result. What we done? We took a training set with 350,000 documents. We built map 300 by 300 clusters, and we set limit by 10 documents. And as a result, we obtained compression of our training set by 18%. And moreover, we obtained improvement in quality. It means that these documents, these 80% of documents, degrade our quality, the degraded quality of our ranking. And you see that original quality of original formula built on the whole set of data is 70.20, yeah, and the quality of model built on the compressed training set is 70.26. But this solution still has problem because the compression is not big enough. We want to achieve more compression, and as a result we constructed algorithm that merge both ideas. This algorithm merge ideas of queue-back and idea of some filtering, I can say. And the first step, we how you remember, QBack algorithms say us nothing about how to build initial training set. You can do it randomly, but it's not the best choice. Instead of, we propose following algorithm. The idea of this algorithm is following. We select some points from our ranking formula, just random points, it's not matter. We take big amount of these points, and we build initial clustering. After that, we select pool of queries just from stream, and in this pool we try to find queries that have a lot of information. How we do it? First of all, we mark each cluster in this map as unused. It's just a sign that we have no documents from this cluster now, and we count how many unused clusters are covered by documents from query. Yeah, and after that, after we count, we select queries that cover maximum, and for each cluster, we select only one document from this query. After that, we recompute the coverage. Yeah, we're looking for the queries that bring us a lot of new information with respect to previously selected queries, and we repeat this procedure several times. We select about, in our environment, we selected about 100 queries as the first step. And then at the second step, we build it. We run iteration of QBack, but we do it in batch mode. How we do it? First of all, we build a committee of models. We already have some training set, yes, and we build a committee of models. After that, we build a new version of clustering for this data. And again, we use the same technique. We mark all clusters as unused, and we start to process queries in some pool. We take several thousand of queries and process these queries. And for each query, we select pairs that have disagreement in committee. Do you remember the idea of QBack? And for each selected pair, we check maybe we seen this pair in previous query. It means that we filter, using this SOM map, we filter out pairs that was already found. Is it clear? Clear idea, yes? No? Okay. I try to explain again. We have pool of queries, yes? Is it clear? After that, we process each query in this pool, and for each selected by QBack pair of document, we check maybe we found this pair. In order to do it, we take clusters of documents in this pair, and if any of the cluster is unused, it means that we have no documents from this cluster in this query. We select this pair. We select this pair, we send this pair to our assessors, and put documents of this pair in our training set. After that, we mark cluster as used, and repeat this procedure for a lot of queries. After each query, we reset cluster labels. And this algorithm demonstrates only one iteration. And how you can see, we build committee only one time per iteration. And actually, this algorithm, complexity of this algorithm is quite big, because we need to process a lot of pairs, and we need to build a lot of models. In our environment, committee size is about tens of models. But it's not a problem. In our environment, one iteration requires about 1 day of computing computing time, and it's not a problem because we need about 1 week to assess all documents selected in this iteration. And the next iteration of algorithm is repeated only after the week. It's a little bit long process, but using this algorithm we can significantly reduce time that we need in order to construct training set for ranking. And I want to show you results that was obtained on synthetic data. On this image, horizontal blue line denotes quality of ranking formula. Vertical axis is DCG metric, classical DCG, and blue line demonstrates quality of model that was built on the training set with about 300,000 documents. It's not very big, actually just experiment, it's not a production data. And green line demonstrates quality of complete QBack plus SOM algorithm. You see that first of all, no. There's no laser. First of all, we see that the first point is the quality of initial training set. In the case of random sampling, it's significantly smaller than quality of training set obtained by our smart algorithm. Yeah, and this fact proves that we have problems due to density. And after that, we see that convergence of the QBack plus SOM algorithm we obtain having only 10% of original training set. We need about 30,000 documents in order to achieve the same quality as on 300,000 documents. And if we remove our technique with clustering, if we remove checking of duplicate pairs, we will obtain also the pure QBack algorithm denoted by black line also works. We have a little bit smaller convergence and as you see, the result obtained by random sampling is significantly worse, and I think that this plot, a little bit synthetic, demonstrates that our algorithm work. And in practice, the last slide I want to show you is the quality of our search engine during the time with respect of to our main competitors on the market. And at the middle of 2012, you see a big gap, and this gap is the release of our ranking formula that was built with active learning technique. And in order to collect training set for this formula, we needed about half a year, and I think it's very fast because at that time we had only tens of assessors, not very big actually. But this ranking formula shows almost the same quality as the quality of our one main competitor. I don't want to say who is who in order to save intrigue. One interesting point about this plot is the rest of quality that we need to improve in order to achieve quality of our first competitor. Yeah, is not due to problem in ranking formula. The major problems are related with, for example, index quality. We have no good documents, and our competitor have, and related with some linguistic problems and so on. There are a lot of problems, but it's not a problem of ranking. Our ranking formula, I believe, that is very good. And that's all what I want to talk to you. Thank you very much for attention. Question, please.